Okay. Continuing with section 10.4, how do you use these equilibrium concentrations? First, how do you interpret these values? All right. So we talked about before, you see sulfur dioxide and oxygen are reacting, and at equilibrium, you see that their concentrations have diminished. However, the sulfur trioxide that is formed by their reaction has increased. All right. So at equilibrium, the amount of sulfur trioxide is dominating the amounts of sulfur dioxide and oxygen. That means essentially it has gone to completion. The numerator value, which is the product, is very large, and therefore the Kc has to be large. All right. Okay. So this shows that at equilibrium, it's mostly products. Most of the reactants have been consumed. All right. So if the values are of Kc are large, it indicates a large amount of product. If it's small, it indicates a larger amount of reactants, which means that not much of the reactants have become products. All right, it hasn't gone anywhere. That reaction is just not very productive. Okay. So that numeric value doesn't affect the rate of equilibrium, how fast it gets to equilibrium. All right. It simply tells you at equilibrium what the composition of that equilibrium mixture is, whether the products are dominating or the reactants are dominating, or there's an equal amount of reactants and product. Okay. So this number, which is much greater than 1, indicates that the numerator is more. That's why the Kc value is more. So it's mostly product. Okay. Here, it's much less than 1. That indicates that the denominator is a greater number, and therefore it's mostly reactants. All right. And that's a good thing because we don't want nitrogen and oxygen in the air forming nitric oxide. All right. So most of the time it's not productive. A very small, minuscule amount of molecules form nitric oxide in air. All right. So for nitrogen and oxygen at equilibrium, it's still nitrogen and oxygen mostly. A little bit of nitric oxide, very, very little. All right. Okay. So that's why the Kc is small. So Kc is almost 1, means that there's an equal amount of reactants and products in the equilibrium mixture. So the reaction is kind of a moderate reaction. It's going both ways at an equal rate. Okay. If it is very large, that means it's skewed more towards product. It's going more towards the product side. If it is small, then that means very little of the reactants are getting transformed. Okay. So these numbers are showing you what's present in the equilibrium mixture. This number is much greater than 1, so mostly products. All right. Anything greater than 1 is mostly products. Anything less than 1 means it's mostly reactants. All right, so once you're given a Kc number, the numeric value, you're also given the value of the products, the concentration values, and say one of the reactants as well. All right, like here, carbon dioxide concentration is given, carbon monoxide concentration is needed, so one of the products is needed. The hydrogen concentration is given, and the water concentration is given, steam rather. So apply this to the equilibrium expression, all right, and manipulate it so that because initially Kc, if you look at the Kc expression, it is going to be CO times H2O divided by CO2 times H2 in the denominator, CO2 times H2 in the denominator. Now, if you move all the denominator to the Kc side, then you can then manipulate that expression, Kc times the CO2 times H2 divided by H2O concentration. And that's what you see here, gives you the concentration of CO. So for each Kc, indicate whether the reaction mixed at equilibrium contains mostly reactants or products. So this is very large, so it's mostly products. This is less than 1, so mostly reactants. At equilibrium, the Kc value is given, the PCl3 and the Cl2 values are both given, and what's the concentration of PCl5? So PCl3 times Cl2 divided by PCl5, that's the Kc, all right? So I would take PCl3 times Cl2 divided by the Kc, and that would give you your PCl5 value, all right? So 0.10 squared divided by 4.2 times 10 power negative 2, okay? And that's the value of concentration for PCl5. All right, let's see if we can do sum of 10.5 as well. All right, so 10.5 is dealing with Le Chatelier's principle. That is, if you put some kind of constraint on an original equilibrium, then what will happen is the equilibrium will shift so as to re-establish a new equilibrium. So you have tank A and tank B with equal levels of water. Now you added more water in tank A. So what happens? The water level in tank B, the product side, has to go up until some of that reactant side comes down, the product side increases, and a new equilibrium is established between tank A and tank B. So imagine this to be the reactant. You add more reactant, you're going to get more product. All right, you have to get more product in order to re-establish a new equilibrium. Okay. Now, if you had removed some of this water, some of the reactant, then of course what would have happened is some of the product would have to break down to replace that reactant. All right. So therefore, again, a new equilibrium would establish with the product level going down and the reactant level coming up. All right, okay. So removing the reactant would make it go in the reverse way. Adding reactant would make it go towards product. If you remove the product as soon as it formed, then it would propel the reactants to form more product. All right, okay. So removing product would make it go forward. Adding product would make it go reverse. Adding reactant would make it go forward. Removing reactant would make it go reverse. Okay. So if you add more reactant, it'll go forward. Okay. So the rate of forward reaction will dominate. And that's what you see here in this picture. You just added a little bit of hydrogen. So initially you had some amount of hydrogen iodide, 1, 2, 3, 4, 5, all right? And then you added more hydrogen, so it reacted with the unreacted iodines. And now you can see that you have more HIs, all right? So 1, 2, 3, 4, 5, 6, 7, all right? So 2 more than what was there before by adding that extra hydrogen, all right? So product concentration will increase when you add reactants, it will go forward. Okay, if you remove some of the hydrogen, what will happen? So think of this as a void, all right? So for example, if I just cover this up, this area up, all right? Then you think of it like a hole that needs to be filled. So more of that HI has to break down to fill up that void, all right? So therefore, it is going to go in the reverse direction. If you add HI, also it makes it go in the reverse direction, all right? Okay, because you've added too much of it, too much product, so it has to break down and form the reactants, okay? So it's the opposite. If you remove the HI, so if you remove some of the product as it forms, then again you're creating a void that needs to be filled up with more product, and so more of the reactants will break down, so it will go forward. Okay, So if you increase any of the reactants, then it's going to go forward. All right. If you decrease the reactants, it's going to go towards the reactants. If you increase the product, all right, it's going to go towards the reactants. If you decrease the product, it's going to go forward towards the product. All right. So table 10.4 summarizes quite well the effect of concentration on equilibrium. So the effect of a catalyst is it doesn't do anything to the equilibrium. It just makes it get there faster. All right. So the time to reach equilibrium becomes shortened. Instead of taking like the hydrogen iodide formation reaction, instead of taking 3 hours, it will take the time, bring the time down to an hour and a half or an hour. All right. So instead of 3 hours to reach equilibrium, it will get there in an hour. All right. So it doesn't change the equilibrium mixture. The equilibrium mixtures of reactants and products will still be a constant. However, the time to get there gets shorter. Okay. So changing in volume. Now gases are susceptible to changes in volume because then their concentration, all right, their density per square inch decreases, all right, or increases depending on what you do with the volume. So if you apply a lot of pressure to a gas, what happens is you're decreasing the volume, all right? And so you're making it in a stay in a confined space. So it wants to release the pressure, all right? More moles, like over here, there's 3 moles, all right? More stuff, more pressure, all right? Less moles, less pressure. So if you decrease the volume, that is increasing the pressure, it wants to go in the direction of less pressure, which is less moles, all right? So decreasing volume means it goes towards less moles, okay? So the vice versa is true. Increasing volume means it goes towards more moles. Okay. So you see here you have carbon monoxide and oxygen forming carbon dioxide. Okay. So if you decrease the volume of this container here, then you're stimulating it to form more carbon dioxide, and you can see that the carbon dioxide concentration increases. If you increase the volume on this, like you brought the piston up, then you're stimulating the carbon dioxide to break up and form more carbon monoxide and oxygen, and you see that the concentrations of carbon monoxide and oxygen go up, whereas the carbon dioxide concentration is diminished. All right, linking this to health, specifically hemoglobin. Hemoglobin has a affinity for oxygen which is pretty high, so it combines with oxygen forming a oxyhemoglobin complex. All right, now this is then through the blood. Okay, hemoglobin is a blood protein and it's transporting the oxygen to the cells in the tissues, and that's how then oxygen level in the cells are low, so oxygen diffuses out from the blood into the cells. All right. Right. So initially, the oxygen levels in the alveoli of the lungs are very high, all right, whereas in the blood it's lower. So therefore, oxygen will diffuse from the lungs into the blood, combined with the hemoglobin of the blood to form HbO2. Okay. So this goes forward in the lungs and the blood because of the fact of the different concentrations of oxygens in the lung and blood. All right. Where in the tissue the oxygen concentration is lower, then this breaks down so as to supply the cells with oxygen. All right. Okay, we'll stop here and continue this in the next video.